Continuing now with the section 2.7 notes, we'll look at example 6 for a couple of examples of the vertical stretch or shrink, and we'll return to our familiar absolute value function since it's a very simple graph and illustrates these rules quite nicely. The graph of f of x equals absolute value of x is shown below. Graph the given function. First one is 2 times absolute value of x. Now that in this case would be y equals 2 times f of x. So here it's a multiplication by 2, and since 2 is greater than 1, that's going to be a vertical stretch where the points are going to move away from the x-axis. Each point will move twice as far from the x-axis as it was originally. For example, the point at 1, 1 will move up to 1, 2. The point at 2, 2 will now move up to 2, 4. The point at the origin will not move because 2 times y equals 0 is still 0. So you see the points get moved by different amounts, and some points don't move at all. And the net result is this vertical stretch, and then points to the left of the y-axis, points to the left of the y-axis will behave in a similar fashion as like so. So that's a vertical stretch. The second example is a vertical shrink because the multiplier here is less than 1. This is y equals 1/2 f of x. So here the y coordinates are going to be cut in half, which moves them towards the x-axis. For example, the point at 1, 1 would now be at 1, 1/2. The point at 2, 2 would now be at 2, 1. The point at 4, 4 would now be at 4, 2. And you see how all of the points get pulled towards the x-axis. Still going to be a V shape, but it's going to be much flatter than before, hence the name of vertical shrink that's given to this particular situation. And then the points to the left of the y-axis will behave in a similar fashion. Notice again, the point that was at the origin does not move at all, because if you take 1/2 of y equals 0, again you get 0. So here we see a vertical shrink. So the stretch occurred with a greater than 1. The shrink occurred with a less than 1, where a was equal to 2 in part A and 1/2 in part B. Now in example 7, let's look at a couple of examples where we just try to produce a rougher sketch of a graph to get a general idea of what it looks like without plotting too many specific points. First example is -3 cube root of x. Our parent function here is f of x equals cube root of x. And recall from the previous section, the shape is similar to that of f of x equals x cubed, but it's sort of like it's lying on its side. It has more of a horizontal orientation. That's the cube root function. What we're dealing with here is y equals -3 f of x. So there are actually a couple of things going on here. First of all, the negative sign is going to be an x-axis reflection. The 3 would give us a vertical stretch. So all of the points get stretched 3 times as far from the x-axis as before. So we are combining an x-axis reflection with a vertical stretch. If you put those two things together, the basic thing you're going to see is something like this. So it's getting pulled away from the x-axis, but also it's reflected across the x-axis. That's the combination of having the 3 and the negative sign. So the negative 3 is a vertical stretch with a reflection across the x-axis. Second example, the parent function here is f of x equals x squared, the parabola with vertex at the origin. The transformation is y equals 1/4 times f of x plus 2. So let me just sketch in the basic parabola that we know from the squaring function, something like that. The x plus 2 shifts that parabola to the left 2 units. So the vertex would now be at -2, 0, rather than 0, 0. The 1/4 is a vertical shrink factor. That's because we're multiplying. And I see in the, I just recognized this, that there's no, oh no, I'm sorry, that's not necessary. Never mind. I thought something was missing from the equation, but it's fine. I got confused there for a second. That happens to me quite often, actually. The 1/4 is a vertical shrink, so that's going to pull the points towards the x-axis. So the net result of these two transformations is a shifted parabola 2 units to the left from where it was originally, but also it's going to open wider. More like that. And then the same too as it goes to the left. So that's the vertical shrink factor of 1/4 coming into play. It's going to give you a much wider parabola. I may have exaggerated how wide it would get. I'm just guessing. But it gives you a general idea of what the graph's going to look like. The vertex would, as I said, would be at -2, 0. That's not real obvious from my sketch, but the vertex would be right here at -2, 0, just so you're aware. In our final example, we're not given an equation for our function. We're just given a graph of a generic function g and asked to graph the function 2 times g of minus x using transformation rules. So what is indicated by 2 times g of minus x? The minus x should produce, according to our previous results, a y-axis reflection. When a minus sign is applied to the x within the function, that produces a y-axis reflection. The multiplier of 2 should produce a vertical stretch of the type we saw in our earlier examples. So we have a combination of 2 transformations being applied to the graph of g. And actually, you can apply the transformations in either order. The order doesn't really make a difference here. So I'm going to first apply the y-axis reflection and then the vertical stretch afterwards. So what's going to happen with the y-axis reflection? Basically, the points that you see on the left are going to be reflected across the y-axis the same distance that they are, but on the opposite side. And basically that's accomplished by just taking the opposite of the x-coordinate. So -3, 1 would move to positive 3, 1. Let me see, do I have time? Let me actually just put in the original graph, kind of indicate what that would look like here. Let me just put the points here to start with. So we have negative 3, 1, negative 1, 3, and 4, 5. Okay, these were the original points, and I'll just put in a dashed line. So I'm just reproducing the graph from the left there so you can see it. Let's look at what the reflection would be across the y-axis. Negative 3, 1 would move to positive 3, 1, same distance across the y-axis. Negative 1, 3 would move to positive 1, 3, and finally positive 4, 5 would move to negative 4, 5. So all those points are moving the same distance across the y-axis from where they were originally. And again, this is not my final result, so I'll use a kind of a bigger dashed line here. They're going to still be connected by straight line segments. Try the best I can to make them look like straight lines. Now, I didn't quite do that right. They should, the two graphs I've shown should intersect right on the y-axis, and mine don't. But I think that's probably good enough. Let me see if I can maybe make that look better. Just bear with me a moment. Okay, so here's the original. Would be crossing about here. So the new one should cross right at that same. Well, I still didn't do very well. So that'll have to do. Okay, that's good enough. And then, so that's the y-axis reflection. And then there's a vertical stretch by a factor of 2, which is going to move the points away from the x-axis. So the point now at negative 4, 5 will now be at negative 4, 10. Twice as far from the x-axis. The point at, let's see, we have positive 1, 3 will now be at positive 1, 6. Twice as far from the x-axis. The point at 3, 1 will now be at 3, 2. So we're just doubling now the y coordinates from the graph we sketched in the previous step. And now again, connect these points with straight line segments to complete the graph. So you see the graph is sketched in stages, and it's really a matter of looking at the specific points that are given and just moving those points individually and then connecting them the same way they were connected originally, in this case with straight line segments. In problems of this type where a specific function, a function with a specific rule is not given, you just are given a kind of a generic graph, usually the points are connected with straight line segments to make sketching the transform graph a little simpler. So that concludes the section 2.7 notes.